All right, let's get at our exam one, problem one. So let's define the directions here. So I'm going to call this 1, I'm going to call this 2, I'm going to call this 3. So for 3, we have our finish minus our start. So our finish is where? It's at 1/2, 1/2, 0. Oops, I want to delete that. Let me get that there. 1/2, 1/2, 0 minus our start, which occurs at 1, 0, 1, leaving us with minus a half. This is going to be a half, and then that's going to be a minus 1. So we're going to multiply that out, and that's going to leave us with 1/2, 1, 2/2. There we go. 2/2 here, not the 1/2 is covered. For 1, we're going to do, let's go ahead and we're going to zoom out a little bit here. 1, our finish is going to be at 1, 1, 1, minus our start, which is going to be at 1, 1, 0. So that leaves us with 0, 0, and then 1. There we go. What about our number 2? It's going to be our finish, which is going to be at 1, 0, 0. Ooh, I'm going to give us some room. And by room, I mean I'm going to do it over here. So our finish for number 2 is at 1, 0, 0 minus our start, which will be at 0, 1, 0. 0, 1, 0, 1, 1, excuse me. 0, 1, 1. So what is that going to give us? It's going to give us a direction that is going to be 1, 1/2, 1/2, the diagonal. There we go. We've got it. Those are my directions. Now, what about my planes? Let me erase, or actually I'm just going to go grab this, erase the whole thing here. I'm going to zoom in. What about here? Well, I'm going to keep my origin. What are my x-intercepts? X-intercept is 1. Y-intercept is a half. What about my z? Z equals infinity. So what's my plane? 1, 2, 0. What about here? I need to switch my direction, or switch my origin. So actually I'm going to go like this. So in my new origin, what's my x-intercept? -1. What's my y-intercept? Y is infinity. What about my z? 1. So that's going to leave me with 1/2, 0, 1. There we go. All right. What are the number of atoms? So atoms in each of these structures. So here, number of atoms is 1. Actually, I'm going to delete. Let me go to my eraser. Delete this because I'm going to be writing these things pretty furiously. All right. Number of atoms, 1, 4, 2. The number of nearest neighbors will be 6, 12, 8. The next nearest neighbor distance will be 2r root 2. This will be also 2r square root 2. This will be 4r divided by square root of 3. The close packed directions will be 1, 0, 0. Close packed directions here will be 1, 1, 0. Close packed directions here will be 1, 1, 1. Close packed planes, none. This will be 1, 1, 1, and none. Excellent. In B, draw BCC. BCC, body-centered cubic, one right in the dead center there. And then calculate the planar density of the -1, 1 plane quantitatively. Also calculate, so we want to draw that as well. So if I have a negative, so I need to go down here, and I also need to go back here. So I probably want to pick something like this is my new origin. So my intercepts will be x -1. So over here, down here, and then 1 here for my y. And then I just connect the dots. Boom, boom, boom. And that's where it'll be. So the tricky thing here, and again, I'm not going to, I'm not going to diminish anyone if they it's very hard to see, but you actually are not going to be slicing through that atom for the 111, those 111 variants here. So you're not going to be able to hit that central atom. So you just have on the corners, here, 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 and then again, that's a third, a third, a third. So you're, actually, excuse me, it's a sixth, a sixth, a sixth. So 1 6, 1 6, 1 6. So that's actually going to be a half. So we know, for example, a sixth, a sixth, a sixth. So my planar density equation is number of atoms, which is a half, times pi times r squared. And then this is our BCC. So A of BCC is equal to 4 times r times square root of, or divided by square root of 2. Divided by square root of 3, actually. And we know that this length here is going to be A of BCC times square root of 2. And we know our equation for an equilateral triangle, the area is equal to, basically, if you call this distance x, square root of 3 over 4 x squared. So let's go ahead and calculate that. One quick second here. Let's go ahead. Yep, exactly. So let's go ahead and plug that in. So that's the whole thing, number of atoms times pi r squared, divided by the area, which is going to be square root of 3 divided by 4 times our x, which is going to be square root of 2 times A of BCC, and then we're going to have that whole thing, that squared. And then it should be this. Let's just take a look. Okay. And let's look at it numerically. This better be smaller than 0.9069, and it is. And we've got it. Fantastic. So we did this. We did this. We drew all those things. Draw the 0, 1, minus 3. Calculate the atomic packing factor of A. So A, actually, I'm going to calculate that first because we know atomic packing, A of simple cubic is equal to 2 times R. Atomic packing factor is the number of atoms, so it's 1 times 4/3 times pi times r cubed. And we're going to get all of that divided by A of Fc cubed, the volume of our cube, and that's going to be this. Fantastic. Draw this direction. So again, we're going to do finish minus my start. So to get the minus 3, I need to have, because we're going to be multiplying by 3, so I'm going to have a 0 and a 1 here, because that'll give it that. And then I need a third, so I'm actually going to do a 2/3 and a 1/3 here, and then I'm going to have a 1 and a 1. So my finish is going to be at 1, 2/3, 0. So this will be my finish point. And then my starting point will be 1, 1/3, and then 1. Yeah. So I'm going to go from here to here. I think that looks correct, approximately. There we go. And we got it. So is there anything left in this problem? No, well, it's very kind on this one. So that is all that we've got. So we'll see you all next time. Actually not next time, in video 2, for our problem 2. See you then. Thanks. Bye.